Yeah. So this questions asked is, yeah, there is one interesting question. Why should all gates be unitary or not required for gates to be unitary? Can one can see example of this? Okay, so one answer why the gates has to be unitary is very simple. Okay, right? So earlier we saw that. Okay, so let me use some new notes. Yeah, right. So just take a quantum state, by the way. What is the nature of the quantum state? The nature of the quantum state is its length has to be unitary. What it means is if I just take a 2-qubit quantum state, a 2-bit state, a qubit state, if I just take, where probability amplitudes must square sum, like their squares must sum to 1. So unitary length. Okay, right? So let's say there is some gate, let's say some gate A, we don't know, let's say there's some gate A, which acts on quantum state psi, should give me some new state which is also has to be quantum in nature. It has to be a quantum gate. It should not be something else, right? It is conserved. If I take a quantum state, I act a gate, it should give me another quantum state. It should not give something else. Because of that, the nature of A has to satisfy some properties that is the unitary property. So that's why if you just take a X gate, X acting on psi, even though it gives a psi prime, this is also a qubit state with with some probability, with probability amplitude, whatever it is started with. Only thing is, in the second case, it is just interchanged. Okay, so only unitary gates which ensures the conservation means the unitary gates only ensures ensures transition of a given quantum state from the quantum state to another quantum state. Okay, so this is a mathematics for you. In reality, you are playing with the quantum systems. It has to remain in the quantum system. You have to carefully tweak with them. So that careful tweaking operation is actually represented by a matrix or a quantum, like a gate matrix, which is actually happen to be unitary matrix. Okay, so that's why all the gates have to be unitary in the first place, right? Okay, fine. So I think gates are need to be unitary because they have probability as one, the quantum state reversible. Yeah, that's correct. That is a exact answer. Okay, sir. Yeah, that's why I did not put my credentials. Okay, so right. So before going ahead, right. So let me show one more gate, right? Before going into the IBM experience, let me show one more gate, which is an interesting gate, which is actually a 2-qubit gate. 2-qubit gate. So far we saw single qubit gate, na? 2-qubit gate. So probably it needs 1 qubit going in, another qubit going on. Let's say there is a box which is a gate, 2-qubit gate. It takes two inputs and it gives two outputs. Okay, unlike conventional classical computing where I can have two inputs but output is only one, but here are two inputs and two output. One interesting property of this gate is what is the need of the top entry, what is the need of the bottom entry is the top entry you can call it as some kind of a control. Okay, right, some control. The bottom entry is a target. Okay, so what it does is depending on the control, the target has to be flipped. Okay, so they will put a symbol plus X and leave it. So this is the gate operation or gate representation for a controlled not operation here. So what I mean is whenever control is high, please flip the target. Doesn't matter. Target is 0 or 1, it has to flip to 0 and 1. If you start target is 0, okay, so it has to become 1. If we start target as in 1, it should become 0. Remember, only when the control is also high. What is high means? The control is in a 1 state. Okay. So this is actually called a controlled NOT gate. If you cross check its truth table, interestingly, if you just take truth table, so let me have truth table for you. Okay. Let's upgrade it. Okay. Drawing. Okay. For a C not gate, I'm just trying to draw truth table. Okay. Right. I have a control. Okay. A target. And I have output C out. I have target out. Okay. Now control is 0 and 1. Control is 0 and 1. Okay. So let me take a target can be two values. That means let's say control is 0, target is 0 and 1, control is 1, target is 0 and 1. Okay. So what I'm saying is when control is 0, target should not do it, target should not, nothing should happen to target. Okay. And control comes out as it is. Okay. Remember, doesn't matter. Okay. Right. Now control is 0, target also comes as it is. When control is 1, target should flip. So always control has no effect on itself. So control is 1, target should flip. Okay. So if you just see this truth table, this is actually exclusively OR gate, XOR gate truth table. Okay. So this is a simple XOR gate truth table in a classical computing. So which means XOR gate is just addition modulo, right? Exclusively OR. Whenever one of them is 1, then only I'll get 1. When both of them are same, I'll not get output. I'll get 0 output. So this is a XOR gate operation. So that is why XOR gate is actually addition modulo operation. Okay. So addition modulo is you take addition of some things and then modulo them with a binary 2. So 1 plus 1 addition modulo is 2, which is equal to 0. 1 plus 0 is 1. 0 plus 1 is again 1. Okay. And 0 plus 0, not just a simple 0, addition modulo 0, which is 0. So this is a XOR operation for you guys. So that's why the C not gate is represented mathematic on the circuit with a like this addition modulo operation, where the top entry here, they call top quantum register, is control and bottom register is a target. Okay. So this is the sorry, 2-qubit gate, which takes 2 inputs and gives 2 outputs. Now question is, what is the representation? So let's say my inputs are 0 and 0. It's a tensor product. It is a 2-qubit state, na? So which is represented like this. Okay. What is output here? Output is also same. Okay, output also represented. So what is the difference I'll get is, let's say when I have a control is 1, target is 0, 1 0. If you just take, so which is tensor product, you can find out, right? Roughly, if I am correct, this is how it looks like. Okay, right? So when you take this as an input, and if you find out the output is 1 1. Okay, so output is 1 tensor 1, which is actually in short form written as 1 1. So which is the mat column notation is 0 0 0 1. Okay, it is there in my notes. You can cross check that. Okay, the C not gate as operation is like that. Now there is a beautiful property you can, like beautiful things you can get out of this gates. Let's say I start with a single qubit which is in 0. I act a Hadamard gate on that. Okay. So 0 becomes a superposition. Okay. Divided by square root of 2 and take that. right? I take one more qubit quantum system, which is again starting with a 0. I act a C0 gate on this. Okay. So what you get here, output mathematically, if you cross check, right? So input state is 0, 0. Okay. And which goes Hadamard on the first qubit, identity on the second qubit, because there is nothing here. You can say there is identity here. Okay. Which gives me what? Hadamard puts a superposition. Okay. And identity does nothing. Okay. Now I have a C0 gate acting on the superposition state, this combination of gate. So C0 gate, as we saw, it needs to one control, one target. Now let's multiply this here itself. You can write this as 0 tensor 0 plus 1 tensor 0 divided by square root of 2. Now I know how to apply C0 gate on this, C0 gate on this. If you apply C0 gate, the control is 0, target is not going to change anything. But if whenever control is 1, target is going to flip. So I'll get output like this. Now I have a two quantum systems, right? Both of them can exist in the state of 0, 0 with equal probability or 50% probability, and 1, 1 with 50% probability. This is an interesting property. It's called entangled system. Entanglement is created. Entanglement. Okay. So what I mean by entanglement is, right? So physically, let's take a simple real world, like a classical example. We can understand. Not able to follow. What is the controlled CO indicating on the output state? Okay. I'll show you the on a quantum experience, IBM quantum experience. Before that, let's try to understand what is this quantum state is all about physically. So what I mean by physically is, I'll take atom A, atom B, put them in a box. Okay. Let's say initially atom A in the ground state, atom B in the ground state. I put them together, create a overall setup. Okay. Let's say they're strictly in the ground. Now I send a pulse of Hadamard gate or a 5 by 2 pulse onto atom A only. Okay. When I do that, atom A becomes a superposition of 0 and 1. So that is what we saw here. Okay. So superposition is created. I'm not doing with atom B, which is remaining in 0 state itself. Okay. So now atom A becomes a superposition. Superposition. Okay. Let's say this is atom A. Atom B in the just ground state. Okay. So this is a box now. Now what I will do, I'll send another pulse of photon, the interesting pulse of photons or some other effect which I'm going to create. So that effect is such a way, so this pulse is going to act with B by checking with the atom A. Like ask, it's like atom A is the owner. This guy will go and ask, can I talk to this atom B? Okay. So whenever his mood is 0, you say, no, just leave it. Whenever his mood is very good, you go and talk to this guy. Okay. So whenever this energy comes in, let's say this energy in such a way that it's not a pi by 2 pulse, it is a single photon, let's say, it pushed the 0 to 1. Okay. So that is what I have created here, a superposition state of 0, 0 and 1, 1. Now, what is the physical implication of this quantum entangledness is, physical implication is the interesting thing. It's like you, okay, 1 minute. Okay. Physical implication is, okay, I'm just doing this. Let me take new notes. Okay. Yeah. Physical implication is, let's say I have 0, 0 plus 1, 1 divided by square root of 2. Remember, the first entry is system A, second entry is system B, first entry is system A, second is system B. Now, There is one property in quantum computing or any quantum systems is, let's say I have a superposition state like this. Okay. Let's say I have a superposition state like this. Right? When I'm like, it's a superposition means what? Atom is doing hopping between ground and excited. Okay. Now it is like a something it is hopping. I just put a stick in between. I'm just go create a wall in between abruptly. Let's say I'm going to make an observation on the system to stop it in doing a oscillation. It's like a coin is being tossed. You are going to catch the coin in the middle of the flight. In that case, what happens? System, if it is confined to the ground, means the excited state is crossed or excited state is nullified. If it is false in the excited state, it is the ground state is nullified. Like there is no chance it can go to the ground state or excited state whenever it falls to other state. It's like toss a coin, you try to catch, if it becomes a tail, there is no chance it's become a head. Na? So whenever I make an observation, means put an abrupt disturbance or try to see it, what happens? Let's say if it confined to zero means one is going to be abruptly stopped. So that is what happens when I make observations on the quantum system. Now come back to this entangled system of two atoms, for example, atom A and atom B. Now what it says here, both atoms can be in the ground or both atoms in the excited means with equal probability, like 1 by square root of 2 is the probability amplitude is 50%, probability amplitude is 1 by 2, 1 by square root of 2, which means equal probability. Now, let's say physically I have created such state, two atoms are so mixed up and created that entangled state. Now what I will do, I take that box and divide it into two parts carefully. Carefully divided, that is possible experimentally. So there is an atom A, atom B. Okay. So they are entangled and they are separated now physically. Okay. Now you send this atom B to some place, atom A to one place, some place. Let's say I have atom A with me, and if I make an observations on the atom A, just now we saw whenever I make observations on the one of the atom, its quantumness is going to be nullified or destroyed. It is going to fall under one of the state. How? This is nullified means its a probability amplitude is going to be reduced to zero. That is what the nullification means. Now, let's say atoms are separated into two separate boxes. Even then, their quantumness is remain to the same. Remember, it is not going to change. Physically, they will be separated, but their quantumness remains in the same quantum state. That much care we can take. Now, let's say I make observations on the atom A box, okay, which is having with me. I don't have anything to say on the atom B, so atom A is with me. In that case, by nature of quantum state observation, whenever I make observation, its quantumness is going to be destroyed. It becomes a classical. How? So let's say atom A falls to zero ket state, means its one state is going to be nullified. How it is going to nullify? Whatever probability amplitude multiplying on to that should become a zero. What is multiplying? It is multiplying is 1 by square root of 2. 1 by square root of 2 becomes 0. When 1 by square root of 2 is becoming 0 means what? This is just 1 by square root of 2, not just multiplying to this atom A, it is also multiplying to atom B. Means the even atom B probability amplitude also becomes 0, means the entire state is going to be destroyed. Okay. So entire going state is going to destroy it. What is happening physically is atom A forced to fall into atom A state, zero state. If this falls to zero state, means even though you have not done anything with the atom B, that also falls to zero state. That is what this state is all about, the entangled state. Okay. It is like there are two friends, like two people are there. Person A, let's say Ram and Lakshman, two people are there, you put them together, make them interact, and then when separate them, Ram to one box, Lakshman to another box, and then physically separate them, put them somewhere else, do something with the Ram. Let's say you just do, let's say give some chocolate to Ram. Ram eats the chocolate, he feels happy. Interestingly, you have not done anything with Lakshman. He also feels happy, irrespective of there is no communication happening, but still that kind of a telepathy happens. Okay, so this is very very spooky effect at the distance exists in the quantumness. It doesn't exist in the real world, classical world, because we like, if we say in real world two people are like this, it's like happens in movies only. There is a long back 10-15 years back there was a movie like this. Okay, so this is what the entanglement. Let's say there is a Ram and Ravan. Okay, so this is another kind of a quantum state creation. What is that quantum state is? Let's say 0 1 plus 1 0 is this entangled state. Okay, how should I create this entangled state is, take the same Hadamard gate and C naught gate operation. Instead of starting 0 0, you start with 0 and 1. Okay, 0 and 1, if you start, you will get this state. Okay, maybe something like that. You can cross check. If you get this state, now let's say the two states are like this. Now, when I make observations on the one of them, let's say system A, I make observation, it's one state is destroyed, means the probability amplitude is destroyed, the entire state is destroyed, the other atom is forced to fall to 1. So it is like now Ram and Ravan are separated. Okay, when I just give a positive reinforcement to Ram, let's say share some good news with Ram, Ram feels happy, but Ravan feels other way around, he feels bad because his state is falling into one, not into the same state. So that is a another kind of an entanglement system. Okay, right? So right, so there are various entangled states are possible. One is 0 0 plus 1 1 divided by square root of 2. I can have relative phase. There is one more quantum state, and 0 1 plus 1 0. Just now we saw with the negative sign also I can create a quantum state. So there are four entangled quantum states is possible with the two systems. It is called Bell pairs or Bell pairs. These are called Bell pairs, or also they are called EPR states. Einstein, Podolsky, and Raisen. So these three people have contributed a lot for this entangled systems. So it's called EPR states. So the in the quantum computing, EPR protocol is very very powerful. Sorry, EPR states are very very powerful. Everywhere else, these things are involved. Okay, every quantum protocol, if you just take, creating entanglement and entangled states being used is very very important. Okay, right? So I'll quickly shift over to IBM Quantum and I'll just show you how to do it. Okay, so let me exit the presentation, stop sharing here. Okay, and start sharing my notes. Sorry, my computer. Right. Oh, great. Yeah, right. Okay, now I think I communicated to the organizers to send a message to you people to create an account on IBM Experience, IBM Quantum Experience. You just search IBM Quantum Experience and create IBM ID, and then you can work. You remember, even though this it says it is deprecated, means it is no more supported, but still we can use that to understand the quantum gates operation. Okay, so there is one more, thanks to our Indian government, CDAC. Okay, CDAC is there. CDAC created a similar kind of a graphical interface platform. You can create account even in this. Okay, and you can try to use this to understand. Okay, right. Anyway, it will take some time to log in. So let me use IBM Quantum Experience. Okay, okay, it will take some time. So here you need to apply for a few universe. It will take some time to give your account, maybe a day. But in IBM Experience, immediately you can get the account. Okay, right? So, so what you see here in my screen is a graphical interface where I can realize some quantum gate operations. Okay, so there are some horizontal lines which actually stands for quantum registers. It's like optical fiber, you can think. the quantum gate states are traveling along them. So as of now, I have two gates, so two quantum registers. What you want, you can just start with single, but for every quantum register, there is a classical register. Okay. What I mean is when you make observation in the quantum system, its quantumness destroys and becomes a classical. That classical information has to be stored somewhere. So there is a classical register requirement. Okay. So that is what we see. Now let's say I have a quantum bit state. Always in IBM IBM quantum experience portal, every qubit state starts from zero by default. That is what you see here. Okay, the state vector representation where zero is having 100% probability, that is one probability. Sorry, probability amplitude one. Okay, and the probability is here. I think it is not getting updated. So computational basis, I think it should update. Let me refresh. Okay, yeah, I think yes, probability computational basis, it will come for zero. Okay, right. Now you see zero bit is pointing in the north, so don't confuse with this sphere with a block sphere. It is just like a block sphere. It is called a q sphere. It even allows you to show geometrically the higher dimensional quantum system like a 2 qubit quantum system. Okay, so that's why it is slightly different from that, but we can still use this to understand. Now say the zero bit is pointing towards the north. Okay, now I want to convert 0 to 1. I want to act a x gate. Okay, x gate is nothing but addition modulo gate on a single bit. So addition modulo symbol is there. You just hold it and drag and drop. Okay, now you see 0 become 1. It is shown in the probability amplitude and even in the probability case. Right, now on a q sphere you see 0 which is pointing in the north becoming the south. Okay, beautiful. Now that is a X gate operation we saw. Let me remove, right click and delete. Okay, I want to take a Z gate. Take a Z gate, act on 0 bit. Okay, so initially you see 0 is there, and here also 0 is there, and I'll take a Z gate, act on 0. Right? Do you see any change? No, no change is there, because z does nothing to the 0 bit. Okay, now what we know, z does something to the 1 bit. Okay, first of all I want to have a have a 1. So what I'll do, I'll just take a 0 and convert that to 1. Now I have a 1. Now I have a 1 at this point. Now I take a z gate, act on the 1. Right, carefully you just see this is of a blue color. Right, now see the color change there. Okay, so blue has become a red. Okay, so it is still remaining the 1 bit state, but its phase got flipped to pi degrees. You see the red color. Okay, correspondingly on a q sphere also it is remaining in the south pole, but it is a relative phase, like it's a global phase actually become red. So that is what is shown here on a quantum experience platform. Okay, so we just saw X gate and a Z gate. So there is a Y gate also. Okay, let's me remove Z. Okay, you as you know, Y gate does something for 0 bit. Okay, just take a Y gate, act on. See, 0 becoming 1, and also it is taking some extra phase, which is for pi by 2 phase. Okay, remove that. Now take one bit. So I have 1 bit. Take a Y gate, act on that. So now I should see 1 becoming 0, and also there is a phase acquired, which is 3 by 2. 3 by 2 phase is being acquired. So this is a Y gate operation. Beautiful. So I just saw X gate, Y gate, and Z gate operation, how it does on this quantum simulator of an IBM. So when you create an IBM experience account, you will be able to access some IBM quantum systems. So that is what you can see. There are a list of available systems, and all those things are there. You can explore later. I'll not get into the details much. Okay, right? So most important thing is we want to see some gate operations. Okay, now x, y, z is done. I want to have a Hadamard action. Okay, so let's take a Hadamard action. Put on 0 bit. As we know, Hadamard creates a superposition. Yes, it is creating a superposition. What is the probability amplitude? 1 by square root of 2, which is 0.707, right? So what is the probability? Probability is 0.5, 50%. Okay. What about Q sphere? Q sphere, right? There is a vector pointing along the 0 and there is a vector pointing along 1 also. So in our quantum, in our block sphere representation, okay, when you go back, do we have here? Okay, wait a minute. Block sphere representation, you see, the equal superposition is just one quantum vector. Okay. In the block sphere representation, we have two vectors. One is pointing up, another is pointing down. So block sphere would like helps understand with a single point on a sphere for a given quantum system. But a Q sphere is slightly different, which may give 2 points. So connecting vectors we have to use to understand. Okay. So that is slightly confusing for you as of now. You can put it aside if you want. Okay. So now that is done. Now H also, Hadamard also creates the superposition even when I have a bit in the one state. So the bit is in one state. Now let's say had act Hadamard on that. Okay. See, I'm creating a superposition, right? 0 and 1, but 1 is with a negative phase, a pi degree phase, right? You see, pi degree phase. That's why it's a red color. Okay, right? So you don't see any effect in the probabilities because probabilities is absolute square, na? So you don't see any color change here. And Q square is accordingly. Okay, fine. This is what we saw Hadamard action. Okay, so there are other gates here. We'll come one by one quickly, right? Okay, so now I want to act a C naught gate. Okay, so I want to act a C naught gate. It is a 2 qubit gate, right? So I need to have one more register. Let me act one more register. Okay, so before that, let's see the observation now. Quantum state observation. Okay, so let's say initially quantum state is in 0. Let's put that into superposition. Okay, right? I had put that in superposition. When I make observation, it should fall to one of the state. So observation is represented by this meter symbol. So it is always makes observations on the quantum state. The result state is put into a classical register. You see now, when I make observation, it is falling into one. Okay, how many times it you make an observation? Let's say 100 times you make an observation. Sometimes it falls to here, sometimes it falls to here, but it's a simulator. It is just showing one. If you perform this experiment 100 times on a actual quantum computer, you would get 50% here, 50% here, because it is super equal superposition state is being created. Okay, so that is the effect of this measurement on a quantum system. Remember, when I make a measurement, it is forcing the quantum state system to lose its quantumness, falling into the classical state, right? That is what we see. So this is not getting updated. If you refresh the system, it will update. Okay, right. Now let's remove. Now I want to have a 2 qubit gate. So let's take a 2 bits, two quantum bits, right? Both are in 0. That's why the new basis is being created 00011011. Remember, in IBM Qiskit, the counting is not done from left to right, it is done from right to left. What I mean is, atom A is on the right, atom B in the left. Okay, like that. Okay, now I want to have entanglement creation. So for that, the entanglement creation is done by Hadamard gate. C naught gate is also very important. Okay, this is the entanglement. Hadamard gate is there, followed by C naught gate. That will create a bell state. Okay, these four states I want to create. Let's start with 0, 0. Okay, and create superposition in the top. You see now the top is right side 0 and 1, left side both zeros. Remember, it is still existing the single state, 0 state, the atom B. The atom A is in superposition state 0 and 1. Now you take a C naught gate. C naught gate is, it should do addition modulo symbol on target, depending on the control. So addition modulo gate is actually a dot followed by addition modulo with a connection. This is the C naught gate. Now you see, I have created 0, 0, 1, 1. This is the entangled state, this first entangled state. We saw that. Okay. Let's say I want to create this kind of entanglement. What I do? Just flip the target from 0 to 1. How can I flip? Very simple. You take addition modulo and put it here. Okay. I have a 0, 1, 1, 0. 0, 1, 1, 0. Okay. Beautiful. So I have created all four cases. You can create all four cases. Let's start with 1, 0. Or you can do it 1, 1. You just do both 1, 1. Okay. Right. So take addition modulo and put it here. It's not possible. I have to remove. I have to remove. Okay. Put both 1, 1 followed with the Hadamard, followed with the C naught. You would get 0, 1, 1, 0, 1, 0 being negative phase. Okay. So this state I have created. This state I have created. Okay. So if I have 1, 0, okay. So 1, 0 means I'll have 0, 0 minus 1, 1. So let's do that. Remove this. I'll have 0, 0 minus 1, 1. Okay. Now, as we know, let's do the measurement on atom A only. Okay. When I do measurement atom A only, the other one should remain in the superposition state. But no, when they are entangled, even when they are separated, when you do the measurement on, just let's say I'll do only measurement on the first system. So that forces the other system also falls to the same state, whichever state the first system is falling in the first place. See, that is the beauty. Doesn't matter. I have not done anything on the system B, but that is forced to fall into the same state as the first system. The red color is stands for both are there in the negative phase. Both are there in the same phase. Okay. So this is the effect of entanglement for you. Okay. So apart from this, there are other gates also shown in the this graphical interface. Let me show what are those gates. Okay. So there is a swap gate. Okay, there is a this is a control not gate. So this is removed. That's why it is highlighted. Okay, it's also called Toffoli gate, and there is a XX. It's also called swap gate. Means let's say there is a quantum state psi here, quantum state phi here. I want to interchange them. I just want to cross the path. You just take them and put it in here. Okay, I'll show you. Let's say I have 0 and 1. This is the top one is 0, the bottom one is 1. If I act a swap gate, it just interchanges. See, 1, 0 it has become. That is the effect of swap gate. Okay. Suppose I have a gate action here. I have nothing acting on the system A. So I want to have, for my own convenience, I want to have a identity there. It is not going to make anything. So I have identity. Okay. So now I have a Hadamard gate here. Okay. I have a C naught gate here. Let's say I want to have a separation for my convenience. I want to separate them into layer by layer. I can just take a barrier and put them wherever I want. I can extend the barrier between first qubit and second qubit. Okay. So that is what you can do. Okay. Fine. So let's remove all the gates quickly. Okay. Right. So now we just saw the top layer, and there is a bottom layer. There is a T gate. Okay. So what is this T gate does? Right. So T gate, what is the S gate does? So Z gate we know. There is a T dagger, S dagger. There is a P, and there is a RZ. So there is a square root of x, square root of x dagger, y, rx, ry, r double x, r double z, u. So these are all gates. What is their gate does? By the way, Z gate we know, right? So it is acting 1 0 0 minus 1, na? Right? If you just take that and you just do a square root of Z gate, which is square root of 1 0 0 minus 1, which is actually, maybe I may need a hand note here, but anyway, Maybe I'll just quickly shift over the hand note and then come back. Okay, so just give me a minute. Okay, I hope you are seeing my hand notes. Yeah, right. You are seeing my hand notes. Okay, let's take a new. Okay, right. So Z gate is there. Are you able to see? Not see. No, no, just a minute. IBM Cloud not opening. Yeah, please don't create IBM Cloud account. You have to confine yourself to IBM account. Okay, right? So yeah, it is sharing. Okay, so not able to see my screen. No. Okay, just a minute. So I'm trying to put Z. Okay, it's not showing. No, it is not showing. Okay, right. So there is some problem with my. Uh, okay, S gate is actually square root of Z. Okay, right. So anyway, I'll use. Let me use my hand. No. Okay. Okay. Wait a minute. Let me get back to my system itself. That is better. Okay. Yeah. Right. So in the IBM experience, okay, where is the IBM experience here? Okay. So in the IBM experience, wait a minute. Okay. So there is a S gate is there, na? So S gate is actually square root of a Z gate. To take a Z matrix, do a square root of that Z matrix, you will going to get a S gate. And you redo the square root of S matrix, you will get a T gate. Okay. So what I mean by that is Z gate induces a phase of pi by 2. Sorry, Z gate induces a phase of pi for a 1 cat, and S gate would induces a phase of pi by 2. Means you are taking the square root of Z. Na? And similarly, T is the square root of S. So T gate would induce a phase of pi by 4 for the 1 cat. Let me show you what is I mean by this. Okay, let's do one by one. So let me take a 1 cat. I have a 1 cat. Okay, I have a 1 cat. On the 1 cat, let's act as Z. So when I do a Z gate operation, so it should get a phase of pi. Yes, it is getting a phase of pi. Okay, right? We saw that in our hand notes earlier. Now remove that. Take a S gate, act on 1. I should get a phase of pi by 2. Am I getting? Yes, phase of pi by 2. Remove that. Act a T gate on that. I'll get a phase of 1 pi by 4. See, pi by 4 I'm getting. So, Z gate and S gate and T gate are actually connected. S is square root of Z, T is square root of S. So, relation between S to Z to T is actually 1/4 root of Z. Okay. Now take this. See, Z is a real matrix. There is no need of a complex conjugate there, right? If you take adjoint, it remains just a transpose. But S is actually the S matrix is having a complex number in it. It is in fact 1 0 0 I actually S gate is matrix wise. So when you take a S dagger, I am going to create a one more quantum gate, and even T is also have a complex number in them. So T dagger is another gate. So these are the one family gates belong to one family. And there is a P gate here. There is a phase gate. Okay. What it does is, see, Z is inducing a phase of pi. Na? Let's say I want to induce some other phase. I don't want a pi phase. I want to change some other phase. Okay, so that is what you can do yourself editing. So here pi by 2 value is there. Let's say I want to induce a phase of pi by 3. So you can do that. So any phase you want to induce, you just use a P gate, which is editable. You see pi by 3 phases induced. Not only that, you can play with anything. You just see, not 6. Okay, see, it induces a pi by 6. Okay, that is what the P gate is. Right now, let me remove. And there is a RZ gate. What it does is, about the Z axis means north pole axis, you want to rotate a given quantum state by some angle. What angle right now? By default, it is pi by 2 angle. Okay. About the Z axis, you want to rotate a quantum state. By the way, about a Z axis, you want to rotate a quantum state means it should be on an equatorial plane or any other plane other than north pole. Na? It should be somewhere. So let's say the quantum state is along the x-axis. Okay, let me take that. How should I put a quantum state along the x-axis is, okay, let me take a Hadamard gate. I get the quantum state along the x-axis. On that, I am going to add the RZ gate. Okay, RZ gate by pi by 2 angle. Okay, it is along this. If I along about the Z gate, if I rotate by pi by 2, it should go to this direction, where y direction, 0 plus I by 1 by square root of 2. What it means is 0 and 1 are having a, a phase of exponential I pi by 2, I pi by 2. Okay, so that is what you see. You take RZ, you see, there is a relative phase exists between this and this. Okay, right? Fine. So that is what you can just edit whichever angle you want. You can do something else. Okay. So according that much angle difference, the relative phase difference comes between 0 and 1. So that is what RZ gate does for you. Okay. Right. So there is, let's say it is starting, right? A quantum state is somewhere here. It is in the one state. I want to force to 0. I don't want to use a gate. So I'll take this and put it here. Yeah. Okay. So that is what you mean. You can also edit that to become whichever register you want to become 0. You can edit from here. Okay. Fine. So there is a dot. It does nothing. Okay. There is a if condition you can use for programming. Square root of x dagger y rx ry. Just like rz, you can rotate a quantum state about x-axis, y-axis with some angle. So those are these gates. Okay, right? Now, there are other gates like RXS, these are deprecated, they are removed. So there's something else, you can forget about them as of now. So there is a U gate. U means there is a combination of many gates together. You can create a unitary matrix. Okay, why? Because there is a theorem. Let me quickly show you what is that theorem. It is actually called Solomon-Kitov theorem, which says any quantum gate could be a product of some fundamental grades. So using this theorem, the property is you can realize, okay, you can realize, for example, okay, have a statement somewhere. Okay, yeah, this statement. Okay, let me enlarge this slightly. Okay, okay, quickly fit to 90%. So any unitary gate could be expressed in terms of the existing fundamental gates like Hadamard gate and a T gate and the Hadamard gate. This is for one particular case, like say I want to create a rotation gate of about x-axis with some radiance of pi by 8. How should I realize that rotation gate using some fundamental gates? Like fundamental gates like H, T and H. Okay, you can do that. That is what uh, this theorem helps us to do. Solovey-Kitov theorem helps us to do. Okay. So in IBM experience, you can cross check that. Okay. Wait a minute. Okay. Right. So unitary gate is actually combination of all of them. The first gate is of rotating about which axis with what angle. Second gate, which axis with what angle. Third gate, which axis about which axis with what angle. That is what unitary gate, a generic unitary gate you can create. Okay, you see there are multiple angles. Okay, so you can create. Here it is a three gate, right? You can add multiple also, but as of now, here I have three. Okay, so that is what Solami-Kitavi theorem for you, right? So I urge to all of you to please go through, right? Please go through this IBM quantum experience and try to experiment, even though it is not going to be extended because it is deprecated. There is a new version is going to come, but it is very, very handy to understand. Let's say somebody doesn't want to rely on IBM, somebody wants to go and use our Indian version. This is beautiful. It's called Quantum Universe, right? If you go and log in into this, it is also does the okay the same thing. It helps you to understand gate operations, and also you can implement some quantum algorithms in the system. Okay, right? So yeah, 445, right? So here you can just clear. Okay, so there are three registers here you want to manage. So here things are slightly different. Okay, I want to have only one register. You can type. You want to have only one classical register. You can do. See here, one classical register. Now here I want to act a Hadamard gate. Bring it and drop it. So I have a probabilities. Okay. So there is something else here. The input and output bases are also shown slightly different. How much phase is shown is slightly different. Okay. Compared to the amplitudes are there. Okay, right? So you can just adapt whatever want, like a view wise, whatever you want to see. Now let's get back. I forgot to mention. Let's say this is our graphical interface. I want to write a code. Okay, so in fact this is all like the information of this one is given to the quantum hardware using a machine language called OpenCASIM, the 2.0. So the code is written like this. Okay. When I want to you convert that to understandable language, it is called a Qiskit. Okay, IBM Qiskit. Here it needs a quantum register library, it needs a classical register library, it needs a quantum circuit library. Just like a Python libraries, here also the libraries are there. A NumPy library from Python is required. From there, you can create a quantum register, one quantum register with a label Q, another quantum register with a classical register with the label C, and then there is a NOT gate acting on circuit.x acting on 0. If I just bring H here, automatically the code changes. What you can do, you can just copy this code, okay, and you can run on your Jupyter notebook. Okay, so I did it yesterday. I think I need to relog in, but don't worry, I'll share Jupyter notebook where you can work something with a coding also. Okay. So, and the Solovay-Kitavi theorem helps me to realize a given unitary gate using the existing gates. So for one of the case, I have given the description. You please go through how it is done. In the next class, the mathematical part we will just discuss. Okay, right? So with this, I think the required background. Okay, let me show to go ahead is actually covered. You see, we did check about introduction to this course, classical bit quantum bits. Okay, spin off systems. This is a spin off electron or spin off nucleus system. Photons also we just checked. Okay, trapped atoms or ions or artificial atoms using circuits we just saw. Semiconductor quantum dots also we just briefly discussed, and the quantum advantage, Madam Anindita will take some time later. And single and two qubit gates we just checked. Solovay-Kitavi theorem also we just checked. Okay. I'll share the PPT of Solovay-Kitavi theorem to you people. You can just cross check and understand. Okay. So I quickly stop here because we started late and also we took a lot of time. Okay. So what is the explanation of HTH? Okay. This is only for one of the case. Remember, only one rotation gate about pi by 8 radians. Wait a minute. Is obtained with HTH. Okay, right? So I have a notebook which I have to relog into my. Okay, I have to relog into my Jupyter notebook and then get that. Okay, but anyway, I'll share that in the Canva. You people can go through, right? So in the next class we will discuss. For any gate, we can realize from the fundamental gates. That is what I mean. Okay, right? So in fact, that is the case. If you just click on this and click Hadamard gate, go for information. How this Hadamard gate is actually realized also given information given here. Okay, so you can go and check the reference how Hadamard gate is realized. So it is in fact a combination of gates or something else. So when I say quantum computer works with multiple gates, it's not like that. It's like higher dimensional gates are actually realized out of fundamental gates. That is what Solovay-Kitavi theorem helps us to do. Okay, fine. I'll stop here. We actually overboarded by 51 minutes compared to the regular timetable. I'm sorry for any inconvenience caused to participants. Okay, so this is due to the last minute changes. It will not happen in the future. Okay, so like I said, all the fundamentals required to go ahead are checked so far. I think Ritajit will start from quantum correlations, entanglement, and Bell's theorem. Okay, so I hope it is done, and I'll come back for a quantum parallelism on 18th. Okay, right? So meanwhile, I'll share all my notes and PPT. Also, what should I say? I'll also share my Jupyter notebooks for your reference. So meanwhile, please explore these two ports. Okay, right? So control Z is also there, control phase gate is also there, control Y gate is also there. So control not is just a CX gate, but I can also have CZ, CP and CY. So that is available here on the quantum universe. When you go for algorithms, beautifully all the algorithms are there. We'll check all these algorithms when I come back with a quantum parallelism. Okay, fine. So I'll just hand it over to Satyan sir. Yeah, thank you for all of you for a nice feedback. Okay, right.
Thank you for the session, sir. So I hope the session was good. So everyone can leave now.
Yes, bye bye.
Thank you, sir.
See
Bye
you.
bye.